in this section, we're going to build up the DC characteristics of what the bipolar transistor looks like. So that's the output current as a function of the voltages applied to the terminals, okay, across both of the PN junctions. So to do that, we first of all think about the output collector current, which is IC. That's what we're going to be measuring. And what we really want to do is to plot the output collector current and obtain the DC characteristics. In other words, for example, at least the collector current is a function of the collector base voltage. So that's the first one we'll be doing. And so for that, we need to assume that the emitter current is equal to 0. And therefore, the only thing we're looking at is the collector base diode, okay, the common base. That's all we're looking at if we assume that this emitter current from that first diode is actually held at 0. So that means that we're then only looking at the collector base voltage. And what happens to the collector current as a function of the collector base voltage? Well, if you remember, we've got an NPN transistor and the base is P-type, the collector is N-type. In reverse bias, we are going to apply a positive voltage to the collector base, and in forward bias, we're going to apply a negative voltage to the collector base. And so what we're showing here, this portion here, is minus VCB, and so we're showing the reverse saturation current, because this is applying a negative voltage. Okay, and remember here, the minus IC comes about from the collector current of electrons in the opposite direction for an NPN to the conventional current. So that's slightly different. But here, this is called the reverse saturation current, ISC, and the collector base junction, VCB, is going to be negative when the device is on, okay? So here we can then see this, we should recognize this as simply a diode characteristic for one of the junctions, the second junction between the base and the collector. Other characteristics, if you say, okay, well, that was good, that's when there's this reverse bias applied to the collector base. The reverse bias would mean a positive voltage being applied to the N-type collector. That's how we like our device to operate, but you can obviously have an emitter current coming through the device as well. So if we do that, we need to remember that, because this is really, sorry, this is all going back to equation, the collector current, equation 58, where we've got the contributions of both of the diodes. But on this first diagram here, we're simply looking at the second diode. But then we say, okay, well, what happens when that first diode is switched on? In other words, the emitter current is not equal to 0. So what we have to remember is that we're just shifting the current levels. So we're adding on a current from that first diode, the reverse saturation current, ISC, is small. And so what we have here is the second plot. Okay, this is still showing minus VCB for when that second diode switches on. And here we have now increasing levels of IE. So this is IE increasing. So this is the reverse bias collector base junction, which is called the active mode. That's how we normally operate the bipolar transistor. And as you increase the current, which arises from an increase between the emitter and base junction, you're going to get higher current. You can see by this increasing values of the current flow through the device. But this is plotting minus IC against minus VCB. That's not normally how you would plot a characteristic. Normally it's IC against a positive voltage. So all we have to do is flip that over. And that's shown here, where you've now got IC against VCB. This is still, so this is now the active reverse bias. This is the active mode, where reverse bias is taking place between the collector base junction, and this section here is the forward bias saturation current or saturation mode. So these straight parts here are ideally straight, but actually they do have a small gradient. And if you remember, that's because I said that in fact they increase as you increase the reverse bias on the collector base junction. So that's called base narrowing, as we have discussed. The other thing that is interesting is that this is really plotting only the current, the output current, as a function of the collector base voltage. But in fact, we often want to plot the collector current as a function of VCE, the total voltage that's applied. And the total voltage applied is you have to sum up the voltage on the first, or both of those diodes, the one between the collector and base, and also the voltage applied to the base emitter junction as well. What we've got up here is the current output as a function of the collector base junction. So what we'll now need to do is to add on, in order to plot against the VCE, we're going to need to add on to these curves, or shift the curves, an amount which is related to the voltage applied to the base emitter junction. So an example of that, doing that, is really shown below. If we know that there's various levels of emitter current that are going to be added on to the output current, and go back to that equation 58 to have a look at it, you remember it's only a portion of the emitter current comes through, and we're going to say that the proportion of those currents coming through is 1 milliamp, 2 milliamps, 3 milliamps and 4 milliamps. Then if the reverse saturation current of the emitter base junction is 10 to the minus 12 amps, we're going to need to calculate the corresponding shift in the voltage so that we can then plot VCE. Okay, we want to plot the output current as a function of VCE. So we need to think, well, for each of, if the emitter current is 1, 2, 3 and 4 milliamps, what must the base emitter voltage that's being applied be? So it's really working backwards. So we need to look back to our equation for a diode. This is the Shockley equation again. We've got the reverse saturation current. We're given that in the question. It's 10 to the minus 12 amps. This is what we're calculating, the voltage applied to the emitter base junction for a given amount of emitter current. When we have those values of the base of the voltage, we can then shift the VCB that's plotted by this amount and plot the same current, the overall current, as a function of VCE. So we need to rearrange this equation here for IE such that we can get the value of VEB. So we do that by saying, take the ISE to the other side, IE over ISE, the reverse saturation current, is equal to E to the charge VEB over KBT. Okay, and then we can make ln IE over ISE equals to VEB times 1 over thermal voltage, KBT, and simply then multiply by the thermal voltage such that we have VEB. In fact, from there you can see that VEB is now equal to KBT over E, which is this constant here, 0.0259 times ln of the emitter current, which is different for each value, or it's got various values that are in linear intervals, divided by the reverse saturation current. So if we initially take an emitter current value of 1 milliamp and put these numbers in, you see that you get voltage VEB of 0.537 volts Do the same for 2 milliamps, you get 0.555 volts. You do the same for 3 milliamps, 0.565 volts will be required at the emitter base junction. If you wanted 4 milliamps, then you'd need a base emitter voltage of 0.573 volts. So you can see that all of these are going to have a shift. If you want to plot IC as a function of VCE, you're going to have to increase the voltage along the x-axis by these magnitudes here, which is the VEB value, and you're going to have to shift it more for larger current values. So the shift is larger, the shift in the voltage is larger for example, 4 milliamps than it is for 1 milliamp. What you'll also see is that they're going to overline at the origin, where the voltage across the transistor is 0. Something else that's worth pointing out to you, and that's also specified in your notes, is that the shift in voltage for a linear or for a constant increment of emitter current is not linear. Okay, it comes about from the exponentially dependence on the emitter base voltage. So as you increase the emitter current, there is a smaller and smaller shift in the emitter base voltage on the diode, as you would expect. So this means that if you actually wanted to have a plot showing linear or equal increments in the emitter base voltage, you're going to get larger and larger spacings on your characteristics as you increase the voltage. Whereas what we've got so far here is linear increases in the emitter or in the collector current. So when you have, if you wanted to plot the characteristics as a function of increments to the emitter base voltage that are equal, you'll see that you're going to have a characteristic that actually looks like this, where the spacing in the collector current is getting bigger and bigger as you increase the size of the emitter base voltage. And so that's what really these characteristics are showing, and that's also what's the purpose of the equations and the numerical example that we've just done is to show. So this is the type of equation that you're really this is the type of plot that you would see in a textbook. It's a plot of the collector current as a function of the collector emitter voltage, or one of the ones that you would see at least. The last thing I want to really talk about are the Ebers-Moll equations. And the important thing here is to think about the asymmetry of the doping in the bipolar transistors. So equation 59 is something you've encountered before. It's the total collector current being the combination of the collector base voltage and the emitter base voltage, whereby an amount or a proportion of the emitter current is going to reach the collector current. Okay, so you've got one diode. Normally you've got one diode, the emitter base diode operating in forward bias, and the collector base bias operating in reverse bias, and that's what we've derived. Those are the characteristics we've shown and the calculations we've worked with. But because it's an NPN in either direction, you could operate it in reverse. In other words, as it says here, with the collector base junction forward biased and the emitter base junction reverse biased. And this would then show that instead of having the electrons flowing from the emitter to the collector, in this case, you're now going to have electrons flowing from the collector to the emitter, and instead have a proportion of the collector current reaching the emitter, where alpha is now the efficiency or the proportion that reach the emitter. However, the current gain in this case is much lower, and the question that you'll have written on your notes is why? And the answer to this is again related to the doping, because the doping would be then much higher in the p-type than in the collector n-type. So yes, it's still n-type, but it's not nearly as highly doped as the emitter, And in fact, it would then mean that the whole current flow through the base and the collector would be larger than the emitter current through the collector to the base. So in other words, you're going to look at the concentration gradient whereby the dN over dx normally is larger than dP over dx when you have the emitter base junction forward biased. However, if you have the collector base junction forward biased, this would no longer be true. And that means that you'd end up getting a very large hole current. Okay, so you're going to end up with a large hole current in the base. If you have a large hole current in the base, it means that your efficiencies are going to be much less, and your current gains will be much less. The ratio of the output current, which in this case would be your emitter current, to the hole current. And so you wouldn't choose to operate in this mode. In fact, this is because we've optimized the device doping for forward active mode. So we've got the emitter current being larger. We have the emitter current being larger, or the emitter doping being larger than the base current, the base doping, in order to optimize and maximize the current gain. So these long equations, you can do it the other way around. So you apply the forward bias to the collector base junction, and you get this instead. You get the emitter flow from the electrons are going to go from the collector to the emitter, or some of them will. But what will happen is you'll get a much lower current gain. But together, we call these the Ebers-Moll equations. And from this, you can look at how the devices can be operated in various configurations. So some of you, as I said, will go on to study more about the application of these devices, and others will just be aware of them. But that really brings us to the end of the section on bipolar, and I hope you can see the most important thing is to understand the basic structure, not the complicated advanced structures, but understand the basic structures of the bipolar transistors, whether they're NPN or PNP, and why one might be better than the other. Also look at why operating in this configuration would be advantageous if you wanted to get a large output current and current gain, and really just have an understanding of where the charge carriers are flowing through the device, both for NPNs and PNPs. Okay, so as I said right at the beginning, the three main things to determine your sort of good operating characteristics are going to be this doping level here, the device dimensions, having a long emitter and collector and having a shorter base, and also having a very narrow base width. Okay, so those are the things we need to think about in order to get the current to be amplified at the output relative to the voltage or current at the start of the device.